Problem 15. The graph of the function f above consists of 4 semicircles. If g of x is equal to the integral from 0 to x of f of t, where is g of x non-negative? All right, so I need to find, and I'm looking at my choices, and it looks like it's kind of telling me different areas where g would be non-negative and where it would not be. So what I did, I just tried to start it. I'm actually going to use each of these key points right here. Well, actually, I'll use all the points on the chart. So I'm going to find g of negative 3. I'll find g of negative 2. I'll find g of negative 1. I'll find g of 0. I'll find g of 1. Find g of 2 and g of 3. All right, and so without even finding it though, we're just going to basically be looking at areas under curves. All right, so if I'm using this formula right here, g of negative 3 would be the integral from 0 to negative 3 of f, which is also equivalent to negative the integral from negative 3 to 0 of f. So if I'm looking for the area under the curve from negative 3 to 0, notice that the area under the curve is definitely more negative than positive, so this area would be a negative answer, but it's the opposite of my negative answer, so this is going to be positive. So it is true at this spot that g is non-negative, right? Then g of negative 2, same type of thing. We're going to go 0 to negative 2 of f, which will be the opposite of negative 2 to 2 of negative 2 to 0, excuse me. So if I'm going from negative 2, which is right here, to 0, notice that this area right here is negative again, so the area under the curve would be negative. However, we're taking the opposite of the negative number, so my g would be positive. So once again, that works, right? Then let's try it at negative 1. So I'm going to do 0 to negative 1 of f, which would be the opposite of negative 1 to 0 of f. And if I look at the area under the curve from negative 1 to 0, it's going to be this part right here, which is also all underneath the x-axis, so that's going to be a negative number, but it's the opposite of a negative number once again, so that is also positive, so that is also non-negative. All right, continuing our quest here, we're going to get 0 to 0 of f. Well, the area under the curve from 0 to 0 is just going to be 0. Well, that is also non-negative. Right, then we'll try g of 1. So this time I'll go 0 to 1 of f. So if I look at the area under the curve from 0 to 1, that entire part is above the x-axis, so that will be a positive value. And then g of 2, if I find the area under the curve from 0 to 2 of f, that is once again all above the x-axis, so that will be a positive value. And then the last one, if I find the area from 0 to 3 of f. 0 to 3, there is more positive parts than negative parts, so my answer will once again be positive. So when I checked all of these, they all worked. So I chose choice A because all of the other ones left out too much stuff. So negative 3 to 3 included it all. All right, number 16. If f is differentiable at x equals a, which of the following could be false? All right, well, I do know that if f is differentiable, it has to be continuous. If something's continuous, then the limit has to exist and all that kind of good stuff. So if f is differentiable, it has to be continuous, so that is not false. If f is differentiable, the limit has to exist because in order for the limit to exist, it has to be continuous, so that one does not work. Okay, this one is just another way of saying the derivative that we're used to, and it says the derivative exists. If it's differentiable, yes, it has a derivative. C, f prime of a is defined, which once again means that the derivative is defined. Well, if it's differentiable, that means you can take the derivative, so that one cannot be false. So which leads us to choice E by default, and it just says the second derivative is defined. Just because you can take the first derivative does not mean you can take the second derivative, so it is choice A. All right, number 17, a rectangle with one side on the x-axis has its upper vertices on the graph of y equals cosine x as shown in the figure above. What is the minimum area of the shaded region? So this is a min-max problem, which means we're going to find a formula for area, and then we're going to take the derivative of the area, and then we'll set it equal to 0 so that we can get our critical values, and then we should be able to find where the minimum area occurs and then actually find the minimum area. All right, so this is the cosine graph, and I need to figure out where does the cosine graph hit the x-axis, and it actually hits it at negative pi over 2 and at pi over 2, so that's going to help me out. So basically what I'm going to be doing is taking the area of the cosine graph and subtracting the area of the rectangle. So the area of the cosine graph we can actually use an integral for, it's just going to be the area under the curve negative pi over 2 to pi over 2. It's just going to be cosine x dx, okay? And then we're going to subtract out the area of this rectangle. Well, we don't know how far over this goes, so I'm just going to say it goes over x, and that would go over x in the x direction. And then how far up this is would be my y value, and it does tell me that my y value is cosine x, so that distance up is going to be cosine x. So for this rectangle, if I'm doing length times width, it's going to be 2x times cosine x. All right, so from here, I'm going to just simplify this a bit. We do get to use our calculator on this one, so if you evaluate the integral from negative pi over 2 to pi over 2 of cosine x, you will get 2, and it'll be 2 minus 2x cosine x. All right, from here we do want to figure out where does the derivative equal 0, so we are going to have to take the derivative. So I'm going to get a prime is equal to, the derivative of 2 is 0, and then to get this derivative right here, I am going to use the product rule. So we'll get f prime is equal to 2, g prime is equal to negative sine x, and so we'll get negative f prime g plus f g prime, and that will be negative 2x sine x, and then just simplifying that a little bit, distributing my negative, I'll get negative 2 cosine x plus 2x sine x, and from here we need to find our critical number, so we'll take negative 2 cosine x plus 2x sine x, set it equal to 0, and from here we can actually use our calculator to use the 0 feature. If you graph this, our picture should look something like that for a prime. So I'm looking for where does this touch, and I changed my window just to go from negative pi over 2 to pi over 2 because that's the only part of the graph I cared about. If you use the 0 feature for that part right there, you are going to get x is equal to 0.878. So it didn't, and then at first I was looking at it, I was like, oh no. Well, actually that was a choice, but that's not the right answer. Well, actually, no, that wasn't. X is equal to 0.860. So I was thinking, all right, I got close to a right answer, but not the right answer, so what's going on? When I realized that I found where the minimum area would occur, but I didn't find the minimum area. So now what we need to do is take our 0.860 and put it into our area formula. So we're going to have area equals 2 minus 2 times 0.860 times the cosine of 0.860. And if you do that, you will get an area of 0.878. So our answer will be choice B. Okay, problem 18, this is a great one here. A solid has a rectangular base that lies in the first quadrant and is bounded by the x and y axes and the lines x equals 2 and y equals 1. And I'm going to go ahead and draw that right now. It goes to 2 and up to 1. So that's the solid we're talking about. The height of the solid above the point xy is 1 plus 3x. Which of the following is a Riemann sum approximation for the volume of a solid? Okay, so I noticed that this looks just crazy. I figured out that if we're adding things together, usually we let the integral add things together, so we're basically finding the areas of our Riemann sum, or we're going to be finding areas of rectangles, and then we are going to let our summation add all of those areas up, and that will create the volume. So what we are going to do for this, it's going to be the base times the height of the triangle. And when you're thinking that when we're doing a Riemann sum, what we usually do, if you recall, we draw, this is going to start at 0 and go to 2. So to figure out what's going to go out front of my parentheses, this number out here, we usually always figure out how far do I have to go. 2 minus 0 is 2. And then we always divide it by how many units we're going to spread it into. Well, we don't know how many units, so we're just going to put a 2. We'll put an n. So what's going to go out front is a 2 over n. And then the inside is just always going to be the height of that triangle, and the height of the the height of the rectangle is going to be based on the 1 plus 3x, and 1 plus 3, and then this is where it gets a little bit tricky. Our x value, because it's going from I to n, we will be using an I value there, but since each interval is going to be going by 2s, it's going to be 2 over n, so we have 2 over n on the outside, and we do have 1 plus 6i over n on the inside, and then it's going to be a summation. All right, so what I did though, as soon as I figured out just basic, when I figured out that I'm going to have 2 over n on the outside, I immediately went to choice D, because we've never put anything other than the width of each interval on the outside, and this all of a sudden had an I out there, which didn't make sense. So by default, I just chose D.